This video is looking at the longer answer questions in the first lot of organic questions, and this would be question 1. So cyclohexene, slightly different alkene to normal, but other than that, just a straightforward reaction with bromine. And we're given marks for the mechanism, but we're also given marks for doing the name and type of reaction. So it's 2 marks for simply identifying this as electrophilic addition. That's 2 marks in, which means there's 3 marks available for the mechanism. So it says show relevant dipoles, curly arrows and charges. So we're going to show the dipole across the bromine, and we are also going to show movement of electrons from the middle of the double bond to the first bromine atom, the delta positive, and from the middle of the Br bond to the delta negative bromine. There's no requirement to put any kind of dipole in the CC double bond, so sometimes you will see a delta negative above that bond. Not really necessary. I would perhaps advise not to do that, simply because you could end up putting that on a carbon and getting confused. But sometimes that's done to show an area of negative charge. The next marks on the mechanism are going to be for drawing the relevant carbocation intermediate. So I've just drawn it skeletal. Doesn't really matter whether you do it skeletal or not. Obviously you could just have your CH2. What I wouldn't suggest for a mechanism like this is I wouldn't suggest doing it as a full displayed formula, because it's going to take you a lot of time. And the most important things really are that you have a positive charge on one of the carbons, bromine on the other, and you have a Br minus with an arrow going towards that. And then the last bit will be simply for drawing the product, which I would highly recommend you just draw a skeletal formula because it's a lot easier. And after all, this is a 5-mark question. It's not that many by the time you've already got 2 marks for naming electrophilic addition. So how the marks would be awarded, perhaps it might be 4 marks actually, given the difficulty of drawing the cyclohexane ring, but you would I have seen definitely some mark schemes where you only get 1 mark in total for this whole section of the mechanism, so the curly arrows and the dipoles, and then another mark for drawing the intermediate, and then a final mark for the final product. But there will be distributed different ways in different mark schemes. The important thing is to make sure that you haven't missed any of the important bits out. So part B is labelled as an extension question, although actually the first part of part B is simply a straightforward empirical formula calculation. So you've been given the masses or percentage by mass of 4 different elements: carbon, hydrogen, bromine and chlorine, and from there we can divide by their respective relative atomic masses to get the relative numbers of moles present for each of those. So dividing 36.5 by 12 will give me 3.04 moles of carbon. I'm going to do these to 3 significant figures just to check, make sure I don't miss anything on rounding up. Obviously hydrogen is simply being divided by itself because it's 1 gram per mole. Bromine we're dividing by 79.9, that gives us 0.507, and chlorine we're taking 18 divided by 35.5, which also gives me 0.507 to 3 significant figures. So 0.507 is the smallest number of moles that I have there. So to get to a whole number ratio, I'm going to divide each of the numbers of moles by 0.5 0.507, which gives me 1 mole of chlorine, 1 mole of bromine. 5 divided by 0.507 basically gives me 9.9, and if I take 3.04 divided by that, I get 5.99. So rounding up, because these are 0.9s, they're very close to the numbers, I can round these up to say that I have an empirical formula of C6H10BrCl. So that's my empirical formula. So the next question says, with reference to the mechanism, explain how the additional product forms. So let's just think about what the original product was. So we drew a structure which was essentially cyclohexane in which there were 2 bromines. Now if I was to think of the formula for that, it's obviously going to be C6. In terms of number of hydrogens, if I go around and check, every carbon in the ring is going to have 2 hydrogens attached, except for the ones that have bromine. So I've got 8 there from those 4 carbons, and then there are 2 more. So this would be C6H10Br2. So the only difference is that one of the bromines has been replaced by a chlorine instead, and I'm told that sodium chloride is added to the cyclohexene. So, point of this is this idea that during the mechanism, the carbocation intermediate forms. So at the start of the reaction, chloride cannot be involved at the start of the reaction. So Cl- isn't going to do anything to a carbon-carbon double bond, because Cl- is a negative ion, and the carbon-carbon double bond is a whole area of electron density. So once the first part of the reaction is done, however, we've now made a carbocation intermediate. So the carbon on the right here has a positive charge because the pair of electrons from the double bond is now between the other carbon and the bromine, making the new bond. And so normally in the previous mechanism we would draw the Br- ion produced in the first step as then attaching and forming the dibromo, and now we're trying to explain how the one with bromine and chlorine attach forms. So instead of the bromide ion attaching, it's the chloride ions which are already present from sodium chloride. So actually drawing this out, basically you've answered it. So you could get 2 marks for simply drawing this, because you've referenced the mechanism and you've really just very clearly shown how it forms by the chloride ion attaching to the carbocation. If you wanted to describe it in words, then those are the words that you need to be using. So you need to be saying that chloride ions can attack or bond with the carbocation intermediate. Be really careful that you don't say chlorine. Chlorine is Cl2. There's no Cl2 present. If there was Cl2 present, you would be getting also dichloro. Okay, so you would be getting chlorine also joining on. So in this case, drawing the diagram is better than trying to explain it. But if you're trying to explain it, you need to be talking about the chloride ions and the carbocation intermediate. And that's all you need to say. So this is evidence for this mechanism. This is how we know the carbocation intermediate forms, or it's one of the ways that we know. Last part of the question gives you some information. Incidentally, you are meant to know this information, so watch out. So you are given often mass spec questions involving chlorine and bromine. You'll get more of them as you do organic synthesis next year. And so you're expected to know that chlorine and bromine both have 2 common isotopes. So predicting the number of molecular ion peaks. So basically, just the number of different masses that can form. That's what we're being asked for. And if it says give the mass of each peak, well, if we work out the masses that can possibly form, then we'll be able to work out how many molecular ion peaks there are. So we had an empirical formula which was C6H10Cl Br, but the question also says both organic products. So I'm also going to be looking at how many possibilities I can have with C6H10Br2. So the C6H10 bit is going to weigh the same all the time. So a simple thing I can do to make working out my molecular masses is I can just work out the C6H10 part separately. And if I do that, adding up 6 lots of 12 plus 10, then the mass of this part is 82. So then all I've got to do is work out the possible other masses that could form. So I've got my 82 and I'm going to add it on to either possibilities of 35 or 37 chlorine or 79 or 81 bromine. So what are my options for the first molecule where there is 1 chlorine and 1 bromine? This is kind of like almost like a probability thing, although luckily they haven't given you the percentages of each isotope, so we're not doing a probability diagram. That does come up occasionally. So we could have a combination of a 35 chlorine and a 79 bromine. We could have a combination of a 35 chlorine and an 81 bromine. We could have 37 and 79, or we could have 37 and 81. If I now add all of those up, and I'm going to add them to the 82 that I originally had, then I get masses of 196 in total. The next mass is just going to be 2 more, so it's going to be 198. The next one is also going to be 198 because adding 35 and 81 is going to give me the same as adding 37 and 79, and the last one will have a mass of 200. So far, for the molecule that has both chlorine and bromine, I have got 3 different masses. Now I'm just going to do the same thing for the Br2, although that's much easier because I only have to consider the fact that there are 2 bromines. So all I need to do is work out what the mass of 79 plus 81, 79 plus 79, and 81 plus 81. So those are my 3 options of different masses of bromines joined together, and then I'm just going to add that to my 82 to work out the 3 possible masses. So already I can see that there are also 3 possible masses for the one that has 2 bromines. And all the molecular masses are going to be just like the other ones. They're going to be 2 apart because those are the differences between the masses of the isotope. So the 79 and the 81 plus the 82 from the C6H10 gives me a molecular mass of 242. 79 plus 79 is 2 less than that, so that would be 240. 81 plus 81 would be 2 more than the original one, which would be 244. So therefore, in total, there would be 6 different molecular ion peaks for this mixture of 2 different molecules. So that would be 1 mark, and then the other one would be for showing the mass of the CLBr molecule and showing the 3 different masses of the Br2 molecule. So a bit of an extension, but you are expected to know, and as you move into synthesis, you'll be doing more mass spec of halogenoalkanes and seeing that they tend to produce these pairs of molecular ion peaks usually, or in this case 3 different options, because we've got Br2 or a Cl and a Br.